So Phil is based in Altrincham in the great county of
Cheshire. Well, it claims to be. It might be in Manchester, but we'll debate that later.
He's a great imager. He images all kinds of objects, so planets, deep sky objects, comets, even the moon.
Oh yes, I've done some comets. Yes.
And I think you've taken some of the finest high-resolution ISS images that I've seen.
Thank you.
He also carries out, thankfully, CCD photometry of variable stars, including eclipsing binaries. And he's also actively involved in spectroscopy.
Robin is.
You have some spectrum on your website.
Oh, right. Yeah. Oh, yes. I've got just one of those simple. Yes. Yeah, I've forgotten now. I've got that little grating thing.
Thanks for the intro. Robin will also be speaking. And, of course, Robin is a real pioneer in spectroscopy, not only in the VA, not only in the country, but worldwide. He's been active in the field since 2002, when there were very few amateur spectroscopists at the time. And one of his great contributions in the early days was to help to commercialize the star analyzer, a simple way of an entry-level way of getting involved in spectroscopy. So we owe him a huge debt of gratitude for that. In 2019, he was awarded the Association's Merlin Medal for his work in this area. Robin specialises, amongst other things, in trying to obtain as early possible spectra of transient events, including novae and supernovae, often beating the professionals. So a double act. I think Phil is starting.
Yes.
Over to you.
Okay. Right. This talk this morning is about modelling pulsating stars. That's mathematical modelling of pulsating stars, which is something I've been interested in for the last couple of years. So what we're talking about here is short period, fairly short period variables which actually pulsate. So let me see, which one of these buttons isn't it? Oop, that's the... Right. So we're talking about pulsating stars. Now, obviously the earliest ever variable stars were the mirror stars. We've just had to talk about those. But the Cepheid variables was discovered a little bit later. I think the first mirror star was in 1590 or something like that. First Cepheid discovery, Delta Cephei, 1784, by the guy at the top there, John Goodricke, sorry. And those are very important category of stars. And the primary reason they're so important is this relationship between period and luminosity, this straight line relationship between the period along the bottom there and the luminosity on the y-axis. This was discovered in 1908 by Henrietta Swan. Those pictures, that diagram there is based on stars in the Large Magellanic Cloud from a NASA Space Telescope. So let's think about these pulsating stars. What makes them pulsate? The first theories for the variation in the brightness, at first they weren't thought to pulsate. Initially, the explanation was that it might be due to some binary eclipses. We've had a talk about binary eclipses this morning. So stars orbiting around each other, partially eclipsing each other perhaps, and causing the variation in the light curve. The problem with that was the shape of these light curves didn't stand up to that explanation. The curves were too irregular, they had features in them which couldn't be explained by eclipsing. So this guy, Harlow Shapley, in 1914, suggested it was an intrinsic variation. The star itself was pulsating. He didn't propose a scientific explanation why that was happening, but he did say it's intrinsic to the star. It was left to this guy, Arthur Eddington, famous British physicist, astronomer, to develop a theory of how that pulsation might occur, a scientific theory of this radial pulsation of the stars. And I would go through that. It's called Eddington's heat engine theory. So let's look at how that might work. We have a layer within the star here, coloured in red, and for some reason it's not properly supported by the pressure underneath it. In every star there's this combination of pressure forces pushing up on the star, stopping it collapsing, and gravity forces which want to pull it obviously to collapse. So let's imagine this red layer in the star, for some reason at a moment in time, the gravity force is greater than the pressure force, and it's going to fall. We have a start then of a pulsation process. As it falls, it goes into deeper layers of the star, where the pressure's higher. So that layer is compressed. And I've tried to show that by this layer now a bit thinner. It's been compressed by falling into deeper pressure zones. Now, Eddington proposed that as it falls, well, it'll get hotter. I don't think anyone, if you've ever blown up a car tyre, you know that the valve gets hot as you compress a gas. It gets hotter. He proposed that what happens if the opacity of that star, that's to say, how transparent it is to radiation, suppose it becomes more opaque as it falls and gets hotter. So it falls, it gets hotter, it becomes more opaque, and these little electromagnetic waves that I've tried to draw here find it more and more difficult to escape. So this layer underneath the falling shell, if you like, gets hotter itself because it's now having its energy coming from the core is being trapped. Now, eventually, that pressure underneath our layer builds up enough to push it back out again. So it's fallen towards the middle, it's become more opaque because it's gone up in temperature, it's trapped radiation within itself, and now it's being pushed back out again by the pressure underneath it. And as it moves out and expands again, it cools, becomes less opaque, the radiation escapes, and the whole cycle repeats. So it's called a heat engine theory because this layer is acting effectively like a valve, trapping heat in and releasing it, trapping heat and releasing it, just like happens in a steam engine or a car or an old petrol engine. You've got this valve system trapping heat and releasing it. Eddington didn't say how the process began, but that was his idea. And the key thing about this idea is that as the layer sinks, the opacity or the transparency must reduce. The opacity goes up, the transparency reduces. Now, there's only one equation in this talk, although it's all about the mass of stars, and that's one here, Kramer's rule. So Eddington's theory says, as the layer falls, it gets hotter, and its opacity goes up. We've got a problem here. The rule for opacities has temperature on the denominator. So as the temperature goes up, and in fact it's raised to this power of 3.5, so if I have a layer which gets hotter, it's going to get more transparent, not more opaque. So that's a big problem with the theory. How do we explain it now? What we want is the layer to become more opaque, but it becomes more transparent according to that equation. Now, in the 1950s, this Russian guy came up with an explanation. I think actually Eddington had already hinted at it, and it's to do with ionization of the gases in the star. As that layer sinks, if its temperature range is roughly right for the region where hydrogen and helium are ionized, energy that it's coming into it by it being compressed can go to the ionization process instead of raising its temperature. So what I mean by that is this layer is sinking into the higher pressure region. It's absorbing energy, but it's not going to actually get hotter from that energy. Where that energy is going to go instead is ripping the atoms apart, stripping the electrons off the nuclei. So instead of the energy heating it up, it's ripping the atoms apart and ionizing them. So we've now got round this problem because as the layer sinks, its temperature doesn't go up, the energy goes into ionizing it, but its density does go up because it's being compressed. So now we have the right effect. We have opacity going up, becoming less transparent as the layer falls. So Eddington's heat engine mechanism can now work because of this additional idea by the Russian guy about ionization. Now, I would say that obviously not all stars pulsate, and the reason for that is because this ionization zone has to be within a certain distance of the surface. And ionization for hydrogen and helium takes place over a sort of typical temperature range. So if the temperature range for ionization is too near the surface, it doesn't pulse. And if it's too near the core, it doesn't pulse. So it has to be in the right kind of range. That's why not all stars can use this mechanism to pulse. Okay, so we have a proposed mechanism. And by the 1950s, astronomers could write down the equations of all that mechanism. the physics of it and say, okay, we understand the equation, we understand the physics. The problem was that you can't solve those equations analytically. You can only solve them with a computer. And at the time, they didn't have the computing power to solve them. What they did have was linearization technique, which engineers and physicists had used for a long time before computers to sort of get an approximate solution to a bunch of equations they can't solve completely. And what does this linear analysis tell us? Well, it tells us, first of all, it gives us sinusoidal solutions. So it'll say the only thing that a linear mathematical equation can give you is a sinusoid, like this one I've drawn on this diagram here. In the background is my observation of the light curve for RR Lyra, which clearly is not a sinusoid. But what the linear theory can do is give us the overall amplitude, the height of the pulsation in brightness, and its period. So this sine wave that I've drawn on here is roughly the right amplitude at roughly the right period, but not the right shape. So we've got there, by having the mathematical theory, linearizing it about a point, and then getting this approximate solution which tells us something about the amplitude and period of the stars, but not the light curve, its shape itself. So progress. Got a mechanism, we can do some maths on it, but what we really need is powerful computers to solve those nonlinear equations numerically. And that came about almost in the middle of the 20th century as a result of this Manhattan Project. I don't know how many of you have gone and seen the Oppenheimer film, but during the atom bomb project, they were interested in shock waves and high pressure gases. Whoops. This is a picture of a sequence of photographs from the Trinity's test. That's the first atomic bomb explosion they carried out in the desert near Los Alamos. And there's this dark ring around that. You can just about see, or there's a light one there. And that's a shock wave spreading out from the bomb. And what they were particularly interested with in that project was modeling or writing mathematical models of that explosion technique to get them right for the bomb. And obviously, that project eventually came to end at the end of the war. They developed this general field of mathematics called computational fluid dynamics, which has been used to this day. And this guy here, Robert Christie, who was involved in that project and was actually quite closely associated with Oppenheimer, he'd moved on to Caltech at the end of the war. He'd worked on the project, he understood this maths, and he was looking for something else to do with it. Where could he find some really hot gases in extreme conditions? Well, how about stars? So he worked on theory of pulsating stars. And by the mid-60s, computers, such as this IBM 7090, which I've got a picture of here, were available. This was the one he worked on at Caltech. It was cost $22 million in today's money, pretty much. And it could do 100,000 floating point operations a second. When I did this project, I had got a computer that was 10,000 times cheaper and 10,000 times faster, which gave me a bit of an advantage. But yeah, they managed it. I don't know how on earth they fitted such a complicated program in such a small amount of memory and got it to work. But I came across this paper, well, I should say that I'd got into variable star observing a little bit. I was thinking, what can I do next? I've tried all this imaging. Let's try some variable stars. And I found these short period, high amplitude delta Scuti stars, which do a few cycles in one night. And that really appealed to me. You know, I can see a whole 2 or 3 cycles of a variable star in one night. So I started to observe them. And with my background in mathematical modeling, I thought, oh, maybe you can do that. And I found this guy's paper and tried to work on it. Well, I did work on it for 12 months. In fact, it nearly drove me crazy. It's quite complicated maths, this stuff. He's got about half of what you need in his paper. And the other half, I had to go around to university lectures and talk and watch, get down the physics notes from courses, for university physics courses. Mostly they were okay, but quite often, particularly with the ionization, they'd say, oh, this is how you do just hydrogen on its own, and I want to do hydrogen and helium, and that was a real stumbling block for a long time. solving the equations of hydrogen and helium ionization. But I made it in the end. After 12 months, I have a model which can model pulsating stars in C. Okay. So how does this mathematical model work? Well, as I say, it's pretty complicated. But first of all, think of an onion. We're going to divide our star up into lots of layers. So it can move, and those layers can move radially, so the star can pulsate. So we have n layers, layer capital N at the surface, layer 1 at the core. In the computer, we assign each layer a mass. So we're dividing up the star into a number of concentric shells, each one we've assigned a mass to. And then we have some equations, basic schoolboy physics, if you like, at this stage. I won't go into the really complicated stuff, but let's think about this layer in the middle here, layer I. It's got a mass, it's got a pressure, and it's got a temperature. And the computer's going to update the pressure and temperature with time. The mass stays the same. The radius doesn't stay the same. It can move in and out. The whole point of this model is for a pulsating star. So what's happening with this layer? Well, it's got a gravity force pulling it down. The layers underneath it are pulling it towards the center. So there's a gravity force pulling it towards the center. There's the pressure of the layer underneath pushing it up. And there's the pressure of the layer above pushing it down. Now, if you can remember your school physics, you've got Newton's law, second law, force equals mass times acceleration. Probably most people have heard of that. Well, we have forces here. We've got a net force, basically. If we want to have a force going up, we've got this one and this one minus this one. So we've got two forces, two downward forces and one up. And if we take that pressure force minus the gravity force, we've got the mass, and that's, we can calculate the acceleration, how that thing moves, how its radius changes. The other piece of physics we've got is the radiation flux. So in the core, in this model, there's a constant nuclear reaction rate going on, the mean luminosity of the star. So imagine at the center of the star, there's your big nuclear reactor churning out energy at a constant rate. If this is a 100-watt star, made that number up, obviously, then that core is producing 100 watts of energy continuously. And that radiation transmitted through these layers to leave the surface. So on average, 100 watts will come out at the top. But there's variation, the star's pulsing, so it varies around that average. And the radiation flux flowing through the star at any point depends on the opacity. We mentioned opacity, that's how transparent the gas is to this radiation trying to pass through. The driving force that's driving it through is the temperature gradient, and then that gives you the radiation flux. Now, most people have probably heard of Ohm's law, volts equals current times resistance. You can think of this in pretty much the same way. The current here is the radiation flux passing through the layer. The driving force, or the voltage, is the temperature drop across the layer. So that's what's causing the radiation to flow in that direction. And the resistance is the opacity. So just think of that as a current, a flux flowing through the layer, governed by opacity and temperature gradient. Throw all those equations into the computer, and you can produce a model of a star that pulsates with time. It's got varying light output, it's got varying radius, and so on. So the challenge for us as observers was to observe the magnitude and velocity curves for a star and reproduce them in a model. Now I'd done my bit with the mathematical model, I think. So I had an easy job of measuring the brightness. Robin measured the velocity. These were the two things that we needed to compare with the model. If we could get the brightness curve of a short period variable and how fast it was moving in and out and pulsating, we could test our model against that and see whether we could get a fit. And Robin is going to explain to you how he measured velocity.
Okay, so how are we going to measure this velocity of the surface of this pulsating star? Well, the principle is pretty straightforward. You take a series of spectra over the pulsation cycle, and you measure the velocity of the surface as it moves towards us and away from us as it pulsates using the Doppler effect. And then you can convert that into the coordinates centered on the star, so that we're measuring the velocity, the pulsation velocity, as the star breathes in and out. The velocities we're talking about are a few tens of kilometers a second. So if we want a decent curve, we're going to have to measure these velocities within, say, a couple of kilometers a second. Now that's pretty small. Even with my high resolution spectrograph, we're talking about a shift of a 20th of the spectrograph resolution, or in terms of the image of the spectrum, measuring to a fifth of a pixel. And we have added complications that when you spread the light out so thinly in a high resolution spectrum, there's a huge magnitude penalty. The equivalent brightness of a spectrum at this resolution is 11 magnitudes roughly fainter than the same image. And we have the additional problem that the pulsation period of these stars is not measured in months and years like the Miras, but hours and minutes. So we can't take too long over making each measurement, 10 minutes at the maximum. So the spectra we're talking about are going to be pretty noisy. Additionally, these stars are hot, tend to be hot A to F type stars, and the lines we're trying to measure are going to be relatively weak compared with cooler stars like the Sun, for example. And additionally, because the temperature changes through this pulsation cycle, the spectrum isn't even going to stay constant. It's going to change. The relative strengths of the lines are going to vary. And on top of that, because we're talking about different lines, they'll be formed at slightly different depths within the photosphere. They could be moving actually at different velocities. So when Phil contacted me, I wasn't absolutely convinced we could do much. The good technique to use in these circumstances is called cross-correlation. Effectively what you do, you take the spectra in pairs and you shift them by small amounts relative to each other, and you measure the correlation each time you shift it. And where that correlation reaches a maximum, the two spectra are nicely aligned, and from the shift you can calculate the difference in velocity. This is very sensitive. In fact, you can use this even with amateur equipment to measure a few tens of meters a second, for example, with exoplanets under ideal conditions. It's also very tolerant of low signal to noise ratio because we're using the whole spectrum rather than just looking at individual lines. We can also target specific lines if we want, but I didn't use that in this case. Okay, so the first run, August last year, I took 35 spectra of RR Lyrae, which has a pulsation period of about 13.5 hours. That was 4 consecutive nights, which we certainly wouldn't have been able to manage this August. You can see at the top, there's one of those typical spectra. And then plotted below it is these 83 spectra I took, arranged in phase order and then duplicated twice to make it easier to see. And I think you can just about pick up a little wiggle in all the lines as the star pulsated and the Doppler shift went from red to blue shift. The colour in the plot there indicates the strength of the lines, strengthening from blue to red. And you can pick out that some of these lines became quite a lot fainter as the temperature increased through the cycle. What we can do is we can take a small part of this spectrum and we can animate the 83 spectra, and we can actually see the star breathing in and out. You can see the spectrum shifting backwards and forwards, blue shifted, red shifted, blue shifted. That's speeded up about 10,000 times compared with the 13.5 hour period. What we can do is we can then measure the cross-correlation, measure the Doppler shifts using cross-correlation, and that's the raw data over the 4 days. and we can fold that into a single pulsation period using the period from the light curves, and the 0 phase is the maximum brightness. And you can see the results over the 4 days fit nicely together, and we get a nice pulsation curve. Now what we have to do now is we have to convert that to a pulsation relative to the centre of the star. So the first thing we have to do is subtract off the relative motion of the star relative to the Earth, including the orbital motion of the Earth. We have to reverse the sign because we want to look at the pulsations relative to the centre of the star rather than our measurements from outside it. And finally, we have to apply what's called a projection factor. And this takes into account the fact that what we're observing is the average velocity over the surface of the star facing us, but the pulsation velocity is outwards from the centre of the star. So we only see the full pulsation velocity at the centre of the face that's in our direction. And the pulsation velocity towards the limb are actually directed outwards. So we don't see the full pulsation velocity. So we have to correct for this correction factor. And once you do that, inverted the sign, taken away the offset, we get this nice expansion velocity curve for RR Lyrae. That little bump and dip there is real. That's actually seen in the light curve as well. And finally, we can integrate that velocity to actually show the change in radius with time. And for RR Lyrae, maximum to minimum is about 0.8 of a solar radius. Okay, flush with success. I thought I'd try something a bit more difficult. SZ Lin, this is a Delta Scuti star, 3 hours pulsation period, about two magnitudes fainter than RR Lyrae, so it's going to be noisy. And indeed, here are the 34 spectra I took overlaid on each other, and you can see the noise is a significant fraction of the total depth of the lines. But the cross-correlation technique did its job, and we managed to produce a nice radial velocity curve and convert that into a velocity, a pulsation velocity, and the radius. Similarly, a couple of other stars, BE Lin, another Delta Scuti star with a shorter period, 2.3 hours. There's the raw data, there's the velocity curve. And SU-CAS is a Delta Cepheid with a short period for a Cepheid of about 2 days, and it's believed to be pulsating in an overtone rather than the fundamental. Managed to get a reasonable curve, but there's a lot of scattering here, and I'm wondering whether that's something to do with this overtone pulsation. Okay, so we have the data. Back over to Phil to see how his model fits.
Right, back to the model, yes. Okay, thank you. So, we're going to try and model SZ Linsis, and the thing you need to put in to the model to get it going it's 4 parameters. You need the temperature, the mass, the radius, and the amount of hydrogen. So I found some sources for those, and I have these typical values, which were quoted in the literature. Those are the 4 inputs that I'm going to put into my model. The professional sources do state uncertainties on all these values, so you have got some leeway. They don't know exactly what the temperature is. It looks quite a range of different values for that temperature, quite a big range of masses as well. So you can put those numbers into the model, but you can vary them a little bit to get the best fit to the light curve and the velocity curve. But before I do that, let's just have a look at the data we had. There's Robin's radial velocity data. And then I took some data through just RGB filters. I don't think mine's particularly scientific, but I've got some data through RGB filters for a cycle of SZ Linsis. So we'd got some data on velocity and colour, if you like. And I thought before we went any further, we'd look at. Sorry, yeah, I'll try my best. We're trying to do a quick animation of this, and I hope this is going to work. If I press this, yeah. So combining my colour curves and Robin's velocity, you can actually see what's happening to our SZ lenses. It's moving in and out and pulsing in colour. So that's based entirely on our observations. Okay. Put those parameters in the model, made a few adjustments, not much, adjusted the radius and the hydrogen values from the nominal ones, and then you end up with this from the model and from our observations. So kilometers a second, this is Robin's observation in blue, and the star model here, this is the mathematical equations is coming up with that fit to the data, and my observation of the magnitude, and almost exact fit in that case to that data. And we also did RR Lyra. Not quite such a good fit from the model here, but you do see this long, it's getting the shape right. It's got this long fade followed by a rapid brightening, and the model gets this little dip here where there's something strange going on in the layers of the stars, which Robin also sees in the velocity. Now, this is a model. We can now look inside the star. We're not just constrained to look at what's exactly happening at the surface. So I've got some graphs here. This is a graph trying to show three things on a flat piece of script on a flat screen. So this is time up the y-axis, 7 hours. This is SZ lenses, so it periods about 2 hours. And you can see the radius here, where the colouring stops. That's the outer radius of the star moving up and down in the cycle. And then I've colour coded with depth, velocity in kilometers a second predicted by the model. So as the star is expanding, we're moving forward in time up there and the radius is getting greater, we've got positive velocities, positive radial velocity causing the star to increase. And obviously, as the radius shrinks, those layers are falling again. So we've got blue colours, negative radial velocities. So you can also see that by the time you get down deeper into the star, not much is happening. So it's constrained. Only the surface layers are really oscillating. Once you get deeper into the star, nothing much is happening. This is a plot of ionization. These graph lines here show you the various forms of hydrogen. So you've got neutral hydrogen, H1, singly ionized hydrogen, H2. So that line there, that blue line is H1. Now near the surface, this is the zone of the star, the onion layer, if you like, I talked about before. So this shows you that at the surface where it's relatively cool, you've got neutral hydrogen. As you go down deeper into the star, the amount of neutral hydrogen falls to 0 because it becomes ionized, and the amount of singly ionized hydrogen, which is the red line, goes up. Similar lines for helium. But if we do the animation, this is what the star model is telling us now. Those layers of ionization are moving and pulsing up and down in the star. So there's ionization near the surface, then it goes deeper, then it moves back towards the surface. So those layers, like layer 60 or something like that, goes between being neutral hydrogen, ionized hydrogen, back and forth. Like I was saying in that heat engine model, that is that layer becoming transparent, becoming opaque, releasing and trapping the heat inside the star. Similarly, you can look at the radiation flux across the star. A value of 1 is the average output of the star. So I've written luminosity divided by luminosity of the star. So on average, the star is going to put out however many watts it is. I think in the case of SZ lenses, it's something like 3 times 10 to the 28 watts. And that would give us a value of 1. But with time varying, this is a pulsating or a variable star, we expect that radiation at the surface to change. And this animation shows you in the layers of the star model what's happening to the amount of radiative flux. So at this point in time, at the surface, we're getting about 1.4 times the average. Let's see what happens as time progresses. So see how in that layer around 50, which is where all the action happens with the ionization, there's huge surges and pulses of radiation coming from the core being trapped and then released. And at the surface, we see this value here move up and down about the average as the star pulsates. So, in conclusion, computer modelling of pulsating stars can explain the shape and structure of light curves and the radial velocity. It's still an active area of research today because astronomers are still trying to refine the Seaford variable rules, and they're interested in some discrepancies between the theory and what they observe, and these kind of star models can help them with that. And amateur astronomers can make the brightness and velocity measurements you need to put into the star model, and hence in some way confirm the main parameters of the star. So we started out with that, for example, for SZ Lyncis, that wide range of potential temperatures and masses. The best fit to its pulsations that comes out of the model maybe constrains those values to, more accurate results. And I'm currently writing a paper on this.
One question. Does your model contain any clues as to what kicks off the pulsation?
No, that's an interesting point. What kicks off the pulsation in the model in the first place is an imposed velocity gradient. You just, they're not sort of exactly random. They are. I use the equations in the Christie paper. Basically, you start off giving the star a kick, a 20 kilometre a second kick internally towards the centre. I think it is believed, well, we've had some mention of the HR diagram. These stars are in that instability strip. I don't know whether you're familiar with that. There's an instability strip on the HR diagram, and stars move and evolve. So stars won't pulsate through their entire life. They'll enter the instability strip. And I think that what is actually happening is that the natural motion of the gases in the star is enough to trigger the star to pulsate, because in the model I can start with quite low volume values of velocity, and it will grow. It will grow. So once the star's gone into that region where it's prone to pulsation, natural movement of gas is enough to get it going.
Cool. Thank you very much. Robin, thank you very much. Great double act. Really enjoyed that. So thank you very much.